This is the last part of week 6 of the class Neuronal Dynamics. I've talked about noise models. I would like to link this now to the question of neural coding. We have seen last week that there are 3 different definitions of rate codes, and a particular interesting one is that based on population averaging. Rate codes, however, are not the only coding principles. Imagine that we look at an image like that of the Sydney Opera House. At some point, our direction of gaze focuses and switches onto this image. It's like switching the image on. This is the moment when the image is switched on. Now, one neuron in the brain that we record may fire its first spike here. A different neuron recorded on a different electrode fires the first spike later. Instead of counting the number of spikes, you get in fact a lot of information by just looking at the time to the first spike. This is the first temporal code. If you stop here, all neurons have fired exactly one spike, but you still have information. This neuron fires its first spike earlier than this one. A related concept is that of phase coding. In fact, in some areas of the brain, there's always some ongoing oscillation, which you would see in the EEG, in global measurements of brain activity. Now, again, 2 different neurons. Say the first neuron fires several spikes. If you look, the spike occurs always just before the maximum of the ongoing oscillation. Another neuron may fire here and again here, close to the minimum. So instead of timing with respect to the onset, we have here timing with respect to the ongoing oscillation. This is called a phase code, the phase of the spike with respect to the underlying oscillation. Now let's look at these oscillatory situations. Suppose I give an oscillatory input plus some noise to my neuron, say an integrated fire model, leaky integrated fire model with a threshold. Then we know there's a mean trajectory and the actual trajectory is close to the mean. Now in the presence of the threshold, it could be that the actual trajectory hits the threshold and then we have a spike. Now obviously it's more likely to hit the threshold when the reference trajectory is further up, and it's very unlikely that you would see a spike here, because actual trajectories are expected to stay in the neighborhood of the reference trajectory. Now let's see what happens if we change the noise. So I plot here the noise level of my noisy input, while the periodic deterministic input current is always the same. If the noise level is big, then my trajectory fluctuates wildly up and down. So now, if the reference trajectory does this modulation, my threshold is up here, well, spikes can occur whenever. You don't see the underlying oscillation. So transmitting the deterministic periodic signal is not very efficient. For highest noise level, the reliability of signal transmission is very low. Now let's look at low noise, a point here. The reference trajectory does the same kind of oscillation. The threshold is at the same value, but now the noise is small. Well, the noise is so small that the trajectory never hits the threshold. So signal transmission is really bad. So somewhere in between, there is a regime where the noise level is just sufficient so that occasionally the noisy trajectory hits the threshold. And it does so whenever the reference trajectory goes through the maximum. So there's this optimal noise level for signal transmission. An effect that's called stochastic resonance. To summarize, there are not just rate codes. There are also temporal codes. There are spike timing codes based on time to first spike or based on phase. In the presence of noise, you can understand these temporal codes. For example, using the picture of stochastic resonance, there's a reference trajectory. Whenever the reference trajectory is close to the threshold, then it's actually more likely that the real trajectory hits the threshold. Therefore, temporal information in the input can be reliably transmitted. Spike timing does contain information, despite the presence of noise.